Okay, anyway, so today we are talking about one very special thing we are doing at RapidMiner, which is what we call the wisdom of crowds. And that's crowds, like not coming from Germany, not, yeah, you get it. So talking about Germany, I think there is one thing we can all agree upon. So we founded the company in Germany, so that's my heritage, but there's one thing I think we all as a group here can agree upon. I'm sure you can, I can, we all can, that Germans are the funniest people in the world. Yeah. So of course, if you start a data science platform out of Germany, you really think, what is your mission? What really drives you? And what was driving me all the years actually was to bring back the fun into data scientists. Did we actually lose it at any point in time? Well, not really. Many of us still have a lot of fun sitting down there somewhere in the basement, writing 20,000 lines of our Python code. So that's all cool stuff. Nothing wrong with that. It can be a little bit intimidating though. And I think also it can be a little bit ineffective sometimes. So if you repeatedly solve the same or similar problems by writing the same lines of code, so maybe that is not really the best approach. So that's what triggered actually the idea behind RapidMiner. Can we make things more reusable? Can we actually share all this greatness we as data scientists create every day? Can we share this with the mere mortals out there who are not able to create this? And why this is so important is actually what we as a software vendor in this field call a little bit the race for this mass of people. Because the problem really is that there's like 363 million knowledge or information workers out there, well defined as the people who are using Excel. I think there's actually even more out there who are not users of Excel, but okay, so 363 million people, and then that's the most, that's a large group, and then there's this tiny area, and by the way, those areas are not really like, whatever, in sync here, but there's this tiny area, those very few people, we call them the unicorns. Why? Because they are superstar programmers with a PhD in statistics, and of course they understand every single business problem in the world. Right. I heard they're existing like unicorns. I never met one of those individuals though. So maybe, well, if at all, I meet them here. Good. Unfortunately, a little bit out of balance with the 363 million other people. So maybe we can empower more people, and that's what we mean by bringing back the fun. If you can make this whole thing a little bit less intimidating, if you can empower more people to do data science, then we get a little bit this balance back between the people who actually benefit from data science and the people who can actually provide data science. Okay, so that's what we are doing. That's what also others are doing. That's a noble goal. Unfortunately, it turned out that this is also a very difficult goal. So I have to admit, this is the first KDD conference I am visiting, that's actually crazy, since 2006. So 2006 I was here, not here, but I was at the KDD and presented, by the way, there was a paper around RapidMiner. So we presented it back then. Now I'm here back again 10 years later, and still I have to admit, wow, things got even more complex. How are you dealing, the few of us who are already in industry or still in industry or whatever, how are you dealing with the problems, the daily problems, just communicating activation functions of Gaussian processes around whatever design of experiments, okay, what? So this is a problem. So how can we solve this problem? How can we actually make us better in communicating our data science results? How can we empower more people to create those results? So I would like to show you a quick demonstration about how we approach this whole thing, but at the same time, I would also like to ask you to look out for a couple of problems. I will be a little bit helpful here. I will point out some of those problems anyway later on, but try to find them yourself. Okay, so we will do some data prep and modeling. It's all visual, so you can definitely all follow, even if you're not knowing RapidMiner already, but you will be able to follow. Have a look what we are doing here. Okay. So, what we're doing here. So that's the RapidMiner user interface. So the details don't really matter, but there's this large area in the middle, and we will design processes by dragging data sets from the repository up in the top left and operators from the operators group in the bottom left into this wide area. Okay, let's start with some data. I start with the Titanic data set. So I drag it in. I then connect it to the results on the right. That basically tells the RapidMiner system, this is the result I'm interested in, and then I need to execute it, all right? So let's click this little button here, and I execute it. That's the Titanic data. I'm assuming most of you are familiar with this. So we have a couple of columns there, like the gender, or the age, or the passenger class, or the size of the family. And then there's one special column, survived. This is the one we would like to predict. So, typical machine learning classification task, simple, we all know this. We can have a look into the statistics here, kind of like a data exploration phase now. Let's see, maybe we see some distributions like here. Third-class tickets have been the most frequent ones. Second-class tickets, the least frequent ones. We see the distribution of age. But while we are looking at this, we also can identify some problems. They are like ID-like attributes, like name, cabin, ticket number. We probably want to get rid of this, because that's not going to help us for the model. Then there's the lifeboat. Probably not a good idea to keep this either, because it's very correlated with the label, it's survived. So let's get rid of this as well. And we have some missing values we should handle as well. So typical data quality problems, we know that. All right, back to the design. So we need to get rid of some columns. In RapidMiner lingo, that's called select attributes, because we call columns attributes. Why not? All right, we figured that one out. We basically want to keep all of those, but those ID-like columns and the lifeboat. So let's kick it out. The lifeboat as well. And what else is there? The name, the ticket number. Let's remove them. It looks simple because it's all graphical and easy, no question about this. But again, select attributes? Who would have guessed that? All right, so that's already the first problem here. So we have less data now, looks good, we got rid of those columns. Still, we have those missing values here, like age, for example, has 263 missing values. So that's not optimal. Let's get rid of those as well. Well, let's type in missing. First thing I see is a filter, okay? Maybe not. Oh, here, replace missing values. That sounds promising. Let's throw it in. Some settings here. Which settings? Single, attribute. What was attribute again? Ah, yeah, age, right? So, well, average sounds good. Let's do that. All right, so we execute this process again. And what we can see now is, yeah, we got rid of those missing values in age. So sounds like we make some progress here. We still have some problems with a couple of missing values. Maybe just get rid of those full rows. There was this filter operator. Let's just filter examples. What the heck are examples? Examples in RapidMiner is the name for row. We could have been calling them case or whatever, like, hey, sure, but we didn't. All right, so next thing. So now the data looks good for modeling. What are we modeling again? Ah, yeah, right, we want to predict this column. How do we tell the system that this is the column we want to predict now? In RapidMiner, there's an operator for that, which is called setRow. Good that I know about this. So I drag it in, I make the setting and say now, well, the survived column, am I actually talking bad about our own product? No, it's a great product, but the thing really is, still, you need to know something. Now, we finally made the right setting. The data set looks good. We can start modeling. Let's drag in some decision tree or whatever we want to use, throw it into the process, and press execute for the very last time. So finally, we got the result. Here's our decision tree, and you have a very high likelihood to survive if you're female, have a small family size, and also pay more for the first-class ticket. Good. That took us 5 minutes. What are the problems? So at least you have to detect one problem. So it's easier probably than coding in R if you don't know R, or Python. Okay, so you probably can agree on this, but what are the problems? Just think about talking to your brother, sister, mom, dad, explaining them what you are doing there. Right. So I think the first and biggest problem really is we need to know the right terms. And we call things attribute. Others might call them variable. There is no right or wrong. If I, as a computer scientist, hear variable, I cringe. Because for me, variable has a completely different meaning. Well, I'm trained by now to just accept that out of statistics, the same thing is called variable, but hey, still doesn't make a lot of sense to me. So at least I need to know the right terms. Then I need to understand the data problems. Now I still need to find the right operations. And finally, I need to make the correct settings. Well, it's still pretty complex and not that easy altogether. All right, so I'm not going to talk a lot about the whole platform here because this presentation is actually about the findings we had, how people are using all those processes and what are the typical patterns and best practices we see here. But one of the biggest problems why we need to do something about this is also accelerated, or it's just bigger because we have a huge number of functions. So the whole system comes with 1,500 functions built in. That's a lot, which is great because it gives you all the power and flexibility. On the other hand, it makes things more difficult. So how can we solve this? So the whole idea, and I think that was one of our better ideas in the last couple of years, the whole idea is this concept of wisdom of crowds. We just happen to have the largest user community on this planet for any visual data science platform. So that's quite neat. So we have 250,000, 300,000 people using RapidMiner on a daily basis. And if they do this and they solve their data science daily problems, is there maybe something in those solutions we can learn from? Well, it's pretty, actually it's the normal idea for every data scientist, maybe take this data and learn something from that. Like, well, yeah, that's exactly what we did. So we took all those processes. If you're opting in, you don't have to, but if you opt in, you share those processes with us in an anonymized version. So we're not sharing any specifics about your data, not even column names, nothing. But the structure and the operations you're using, they're sent to one of our servers, put into a huge knowledge base, and then out of this knowledge base, they're giving you recommendations what other people with a similar problem did now in a situation like that. That's what we call wisdom of crowds, and this all falls into this bucket of guided analytics. So this is just so you know what you have to look for. So this bar here, which is here at the top of the slide, you will find it now in the next short video at the bottom of the screen. So pay some attention to this. So those are recommended first steps. Those are the recommendations here on the screen for the empty process. Well, the first recommendation is you should retrieve some data, meaning loading some data into the process. Well, that makes some sense because you want to analyze some data. But we will see how this changes while you're building the process. What I personally, since I know a thing or two about data science, find even a little bit more exciting is the hint about what parameters to tune. So whenever you see this green caret, this little green triangle next to a parameter, this means this is a parameter most users change. And then if you click on this thing, you see also what setting most users are doing. So in this case, for example, that might be K for K-means, I don't know. You see basically what is the distribution of values people are using. All right. So now let's do the same thing, something very similar to what we saw before, but this time with using wisdom of crowds. All right, we start again. Empty process. Pay some attention to the bottom here. It's hard to read from the back probably, but I will explain to you. So at the beginning, it tells you like, well, start with some data, we drag it in. Now it changes, and the first recommendation I'm getting is select attributes, select the columns. Now I see, well, most people change this parameter here. Let's do that. Oh yeah, subset is exactly what we want. It's the most frequently used selection in this case. Let's do what we did before, select all those attributes. So next step now is, after we did this, you can already see it in the bottom here, that set role for identifying what is the label column, the targets variable. We can basically use this operator here, again, make the necessary setting, and we can already see that the next suggestion is filter examples. Well, that's for handling the missing values. You could go with the missing values operator we did before, which I would prefer, but in this case, RapidMiner makes the suggestion to actually filter them out and throw them away. All right, let's do that. Again, this is one of the frequently changed parameters. We throw in the decision tree, and after we did this, the next recommendation we would get is to apply this model on unseen data. All right, the tree looks a little bit different, but that's not the point. The prediction accuracy is pretty much the same. The main point is that took us 45 seconds, and even if I don't know anything about the system, I get the right recommendations, basically always the right suggestion what to do next. And that's not just true for machine learning. Maybe even more importantly, it's true for the data prep phase, because let's face it, that's where we really spend our time. So now getting a recommendation about like, oh yeah, you should really use a k-means here. Yeah, I know. I want to do clustering, and you will see a little bit later that k-means is kind of like a natural choice here in this case. So anyway, we will see this. All right. So this is what the system is doing, but that's actually not the topic of the talk. I just wanted to show you how we collect all the data. The actual topic of the talk is now what is in this data. So is there something we can find? Is there something interesting we can learn from? So the first thing is a couple of high-level statistics. How relevant is this data? So how many people are actually contributing those processes? And I'm very proud that just last month, actually, we hit the 100,000. So more than 100,000 people out of our user community opted into the system and say like, well, I'm fine with sharing my process with you if I get some recommendations back. So I would say, yeah, that's significant. I don't think that we have any other study or any other data set available which describes the behavior of 100,000 data scientists. Okay, so that's, I would say that probably is somewhat meaningful. And how many processes are in our knowledge base? In fact, by now, almost 3 million processes. Well, does that mean that everybody only contributed 30 processes on average? Yes and no. Yes, in the sense of like, yeah, on average that calculation is true, but no, because they actually submit many more, but that doesn't mean that we store all of them. So if you make small variations of the same process, we only store the last one, just as an example. So the reason is just we don't want to store any garbage or anything which doesn't work, for example, is not stored as well. So that's basically what we have in the system. So 3 million different processes. And again, I don't think that there's anything else out there that large describing how data scientists are working today. So now let's look into those processes and also look at the data. That's where we start with the data people are analyzing. So we're not sharing and transmitting any of your particular data sets, but we transmit two things. One is the number of rows, the other thing is the number of columns. Don't send around the column names. We don't even send around the types of the columns, but at least the dimensionality and the number of rows, this is something we share or we collect. So what is the expectation in terms of data set size? Oops. What is the expectation in terms of data set size? So I looked into some polls which have been done by our friend Gregory from KD Nuggets. So I looked into the 2015 poll about what is the largest data set you have analyzed, and people could answer whatever they want to answer. And it turns out that people say this peak here in this graph is somewhere around 10 gigabyte, which for 100 columns, just as an assumption, would translate into roughly 10 million rows, including metadata and depending on what exactly the type of data is. But as a rough estimation, as an order of magnitude, that's probably about right. So 10 million rows is claimed to be the peak here for the largest data set analyzed. So let's have a look into reality. On purpose, you can't see anything here because this is basically the full distribution here. And on the right, at the bottom of this screen, you see that the largest data set analyzed, and this is only data for the past 4 or 6 weeks or so, because we only added the collection of data set size most recently, it's like a couple of months ago. So this is much less data than the full 3 million processes. But still, so 40 million is what is at the right end of this x-axis. So that's kind of the largest data set we saw in those 4 weeks which have been analyzed, okay? 40 million. But that happened maybe once, okay? And then there's 20, 30, 35 million rows, whatever. So maybe we should change the scale here a little bit. Let's put this on 1 million. So now we zoom in, basically. Now we look at the distribution to up to 1 million rows. And still it looks pretty much skewed. So people are actually not analyzing that large data sets as it looks like. Okay, not even 1 million rows. Well, there are people who are analyzing 1 million rows, but not that many. Okay, let's zoom in. Now 100,000. That looks a little bit better, but still pretty skewed here. Can it really be that most people analyze less than 10,000 rows? Yep, that's exactly right. So much about big data. Good that we, by the way, acquired a company pushing down RapidMiner processes into Hadoop clusters. It's still a pretty great product. The thing really is, in most of the cases, people analyze pretty small data sets. Like, wow. And I mean really small. Again, this is just 4 weeks, 6 weeks worth of data. Probably if you would take a whole year, things would look a bit different, but still. So here's the data, the same data in the form of a table, because now we want to figure out, is there a difference between customers or paying customers or between academic users? If somebody is not a customer and we don't know if somebody is an academic, they fall into the other bucket. And to be honest, I don't think there's any significant difference really there. Maybe on the maximum rows more so than not. Average looks pretty much the same. Median is not that different there as well. Interesting here is the 2. Apparently 2 is a very frequent data set size for our customers. Not a huge surprise if you think about how to present some results, some aggregations, whatever. It's actually not really that surprising if you feed some information back into a Click or Tableau or whatever, what many of our customers are doing. So anyway, so it looks really that the maximum was really more like 1 million rows, not 10 million rows. So to answer the original question, what is the poll answers versus reality? It looks when people asked about the size of their data, that they have been a little bit exaggerating maybe, because the reality looks smaller, much, much, much smaller. Well, by a factor of 10x smaller. So that's the first interesting finding. But there's a little bit more. Did you spell this one? 1309. Why is this number occurring 3 times? Anybody, any idea? It is a very common data set. Do you know which one? No. Welcome, the Titanic data. It is the data set which is used by now, for example, on Kaggle as the demonstration data set. It is also the one we use for our own tutorials. So we deliver it inside of the product next to Iris, Sonar, and whatever. I think Titanic's becoming the new Iris. And since Iris was published in 1934, I think it was about time that we get a new one. Okay, anyway, so the Titanic data has exactly 1,309 rows. So that actually made me wonder, and I didn't know. So I saw the 1,309 like 3 times, like, okay, what's going on here? And then we looked into the data. All right, so on to algorithms. Now things get a little bit more interesting. So what are the most frequently used machine learning algorithms out there? So again, let's check our expectations. It's hard to find good sources for that, though. I found again from our friend Gregory some poll from 2011. I just met him here and asked, hey, Gregory, let's do a new one. Because 2011, that is like ages in our field. And he also made a poll basically like using some classes like decision trees or regression. That's pretty broad. So, but at least we see decision trees pretty frequently used, regression algorithms, next clustering, SVM, association, ensembles. And then from the ICDM paper in 2006, here I think the authors asked like 30 experts what are their favorite algorithms and then aggregated the feedback. So, and again, decision tree at the top, K-means clustering, SVM pretty high, other boosts are a little bit lower. So yeah, we get some good feeling about the algorithms. Okay, let's have a look. So here I actually made a little bit different because what I was doing is I was putting things into groups. I mean, what's the point to figure out that decision trees are 5 times more used than K-means? They are solving different problems. Like, why compare them? So I put things into groups. So predictive group, which basically is classification, regression, even that you could argue. Why not separating them further? But whatever. So we have the predictive group here. And yes, in 2016, still decision trees are the #1. Followed by naive-Bayes, KNN, SVM, neural net. And by the way, in RapidMiner you will find random forest, gradient boosted trees, deep learning, but still people love decision trees. Why? Because you can actually explain them to your brother, sister, mom, and dad. Okay? So that's a big advantage. I tried the same with an SVM. Failed a little bit. Okay, so next thing then, ensembles. Error boost, in fact, is the most frequently used ensemble methods even today. But just to put things into perspective here, if you look at the absolute number of usages of ADA boost versus decision trees actually have been used 10 times more frequently. Okay, so that ADA boost is the winner within the ensemble group doesn't mean that actually many people are actually using it. All right, by the way, just in case you wonder, I only showed the top 5 here. I think random forest was actually number 6 on the predictive group, which you could argue should actually belong into the ensemble group, whatever. But anyway. So now, next thing, clustering. Here we have really a very clear winner. Okay, in 50% of all the cases that anybody used any clustering algorithms, it was K-means. When was the first K-means paper published? The 60s, 50s? I don't know. So it's almost disturbing how constant and how stable things stay, actually. Okay, 50% K-means. And here, decision trees was about twice as much as K-means. So just to put things into perspective here. So yeah, I think actually we can say it was pretty close. So this list decision trees, K-means pretty high, SVM pretty high, other boosts at least high on the ensemble methods. I think we can state, yeah, that was pretty much in line with our expectation. And also, in a little bit disturbingly, it was pretty stable over time. I mean, the 2006 paper is 10 years ago, okay? Things didn't change that much. So that begs now for the question, which operation is the winner? Is it a machine learning method? Is it maybe a data prep method? You might have an idea. Which is the operation which is most frequently used? And the winner is our good old friend, select attributes, select some columns. Nothing really fancy here. But it was used in far more than 500,000 of the processes. So actually, if you think about this, you load some data, you want to get rid of half of it typically because whatever. you don't need it. Well, sure, it makes some sense that this one is so frequently used. So let's have a look into data prep then in general. Select attributes is the most frequently used operator, then set role for actually defining the label. Filter examples makes a lot of sense actually as well. First big surprise really for me was cross-validation in the top 5. I'm saying that this is a big surprise because if I read our own community forum and user forum, I'm still surprised how many people struggle with doing cross-validation in the right way, although it's really simple. So at least it's good news for me now that it's actually at least widely used. I hope that people are using it in the right way though, but okay, we will see. Generate attributes, probably also no surprise. That's basically for generating a new column using some formula based on existing columns. Another small surprise for me was actually that sampling is not used more frequently. That I expected a little bit higher, to be honest. But on the other hand, if all you have is 10,000 data rows, why should you bother? Okay. Next thing is extensions. So we have a marketplace where people can package new algorithms into whatever, an extension for the RapidMiner platform. So what are the most frequently used extensions here? So number one is text processing by far. And I'm saying this because, well, this one we see here at the top is our own text processing extension. But then on place number 3, we have one from our partners at Alien in Dublin. And then there's another one, I think it made it on the 10th or 11th place, which is a little bit newer from another partner, Basis Technology in Boston, or Cambridge actually. So the thing is, text analytics by far is the most frequently installed extension, but then of course there are the usual suspects like R scripting and Python scripting for embedding R and Python scripts into the workflow. Vector is still around. Yeah, thanks for the laugh because I thought the same. I love it. I honestly love it. But on the other hand, it's like, what is it now? 25 years. It's around for 25 years. So it's really interesting how frequent Vector still is used. Hadoop is interesting here as well. That is the company we acquired in 2014. That is actually something we only made available to our paying customers for a long time. And only a couple of weeks ago, we made it available to the general public. And despite the fact that people analyze so small data sets, it's already in the top 10. Okay, let's see where this is going to. Maybe we will see larger data sets in the future. Okay, then going a little bit deeper, I was then looking into the processes and trying to figure out what is frequently used together. So what I did was frequent item set mining, some a priori, creating those association rules, and this is what you see here now. So the first thing which was very interesting, that on the left side, those things somehow belong together, and on the right side, things belong together. So we have two groups. And actually, if you look into the detail, you will see that on the left side, we have operators like rename, filter, select attributes, generate attributes, set role. Okay, that sounds pretty much like our pre-processing bucket here. On the right side, we have apply model, performance, cross-validation, naive base. Well, that looks pretty much like a modeling bucket. Why are those two things so separated? And then I thought about how am I working with RapidMiner. Whenever I create a new model or in general work on a project for a customer, I typically separate those steps as well. So I built a couple of workflows and processes to do the data prep, put this onto the server, and actually automate this thing there, use scheduling and whatever. And then while I'm working, or after I prepare the data set, then I can still work on the modeling, try to optimize the model, find the right parameters, etc. So yeah, I actually separate those two things as well, and that's probably the reason why we have those two clear groups. All right, parameter settings. For me personally, actually the more powerful feature. I don't need somebody to tell me, well, yeah, I want to select some columns. I know that I want to select columns, and I also know what the name of the operator is, so I don't need this part. But the parameters was surprising. Let's have a look here. So first parameter I looked into was the parameter C for SVM. So that's basically the trade-off between the, as you probably all know, but whatever, the trade-off between the training error and the complexity of the model. Well, yeah, you should tune that to expect anything good from SVM. For a nonlinear kernel, probably even a little bit more than that. So 0 actually is the default value. That actually means that we are trying to find an optimal value for you. So it makes a good amount of sense that this is the most frequently used value. And then it looks like, it looks more like 10, 100,000 in this order of magnitude. Those are the parameters people are selecting. K-nearest neighbors, another interesting pattern here. Most people, in fact, 71% of the people select a value between 1 and 9. Well, it says 0 here. That's just the way how we visualize it. It doesn't really make a lot of sense to I think it's not even possible to select 0. Anyway, so 71% take a pretty small value, another 14 for take a value between 10 and 19. First surprising thing is, it does actually make a lot of sense that you see any pattern, because doesn't it depend a lot on the data set size and everything else? Like, okay, but I do believe also the fact that it goes up again towards the right side here, it is a little bit like if you take a small value, you make really more like non-linear local modeling, and if you really go with a very large one, you basically end up with a more linear or more smooth decision function. So probably it makes some sense that you see this pattern here. Still, I'm not fully buying that this makes a lot of sense, to be honest. So fault of cross-validation, just to prove the point, like, yeah, people, in fact, 80% of the people go with 10. That's also the standard given in literature, so not a big surprise. If at all, people go with smaller number of folds, not with larger number of folds. Makes some sense. K-means another surprise, maybe even bigger than the k-nearest neighbors. This is the number of clusters you're looking for. And 75% of people select values between 2 and 8. That totally depends on your use case. It depends on the data, that depends on the number of clusters which are in your data. It makes 0 sense actually that there is any specific pattern really. I could argue I have use cases with like hundreds of clusters, but I think people can't handle 100 of clusters, and that's what we really see here is actually more a picture about human behavior than actually what makes sense from a data science perspective. But okay, whatever, it doesn't make a lot of sense to me, but still. All right, so before we wrap this soon, last quick thing here. So what happens with context? So for example, here we have a cross-validation operator you can dive into. And now you see that actually the recommendations change. So for example, I get some modeling operators here. And after I drag in the model, the value for apply model changed to 99%. So if you're at this stage, practically everybody is using apply model as the next step, which makes perfect sense because in the testing phase, you need to apply the model you just trained in the training phase. And then again, the performance estimation as well. RapidMiner has a pretty modular approach here, and the reason is so you can also calculate the effect of pre-processing on your model as well. Another example here is text analytics. Just because we talked about this, I created a simple sentiment analysis case here, a couple of positive and negative texts. If I go inside of this thing now, all the operators at the bottom change now to tokenize or transform case to lowercase, filter stop words. So basically only operators which make sense in this context based on like, well, right now you're working on text documents. So it doesn't make sense to suggest whatever, select attributes. So, and this are all of those kind of things we never told the system. So this is really, that was for me the moment like, okay, it works. It took basically all the wisdom of the people and made the right suggestions here. So if you're a RapidMiner user, that's very helpful, but even if you're not a RapidMiner user and think like, no, I like to sit alone in my basement and not able to talk to anybody else, in that case, still I have a nice tool for you guys. That's something we call mod. Yeah, you're not really good at marketing apparently. So it's called mod by RapidMiner, and mod because it finds the right model for you based on the properties of the data. So you can basically now enter the properties of your data here in the filter list on the left. Like for example, you're working numerical data, you also have some categorical columns there. You also have a categorical target type, thousands of attributes, millions of rows, and then you basically see what are the models and what are the machine learning methods you can actually use on data like that. And that data is also, we got it basically directly out of the wisdom of crowds, basically like, okay, what have people been successfully using? So that's available online, mods.rapidminer.com, so you can basically try it out yourself. That's a quite neat tool, which I think you should have in your toolbox. So last but not least, so why are you still fighting alone? I don't know. You should really go there, download RapidMiner. It's available for free. There's an educational license as well without any limits, so you can basically use it for everything you want. You also should start using mods. I really love this small little tool. And third point, have some fun and success, because I think at the end that is our mission. Let's bring back the fun into data science. Thank you.
So do you use a statistical approach here when you recommend, or you use a more predictive machine learning based?
It's actually a combination. So we overlay two kinds of recommendations. One is actually coming out of the frequent item sets we see, which is working quite well, but not always. The other one, we actually take the context into account and make a prediction what is the most likely best step. This works really good in those context-based situations, not so good though on the overall recommendations. The latter one has the big advantage though that we can take some properties of the data into account as well. So it is kind of a meta-learning approach, if you like, on one hand, and the other one is purely frequent item sets. And we not even bother about association rules. We just suggest what's going frequently with each other. So we don't even look into things like first you did A and B and now it's C. Whatever, if A, B, C occur together and you do A and B, we suggest C. So that's really very simple, actually.
Another question, is it online? If users recommending recommendations, what they're using, and do the wisdom of the crowds get updated as more and more users use that?
Yes. So online has two meanings here. The first thing is actually you have to be online because we are not storing a static model. You actually send your process to our server. We send the recommendation back. And the reason for that is so we can be adaptive and we can make changes while you are using the product. Some of our clients actually say like, well, we would like to have our own knowledge base because we would like to see our own best practices recommended more frequently. We can do that as well. So you can basically set up a server on your own premises and say like, look, you can seed it with what we see in the open source community, but then over time it will actually adapt to how your analysts are working. A handful of customers who are doing this. I think most people go actually just with the freely available open source version of the recommendations.
Thanks a lot.
Oh, absolutely.
One more. Okay. Hi. I have a quick question. So first, thanks is a very interesting data set and a very interesting insight. But I just find it's very surprising that users are, as you have pointed out, users are actually handling very, very small size of data.
Yeah.
Have it ever occurred to you that it might not because users are actually handling very small size data in real life? It's because they are handling very real small size data in RapidMiner. Because I actually look into the pricing page of RapidMiner. Yeah. For free account, user can only handle 10,000 rows at the most.
Yeah.
And if a user wants to handle over more than 1 million rows, he need to pay like over 5,000 years.
2,500, but it's okay.
Oh yeah.
No, that's fine. No, but the point well taken. This new pricing is in effect since 2 weeks. All those data showed to you before. I prepared this whole in July, so this restriction was not existing. Okay. So no, is the answer. That is not the reason the pricing model, but part of the reason why the pricing model is like it is really like, okay, look at that. People actually analyze relatively small amounts of data. And keep in mind, you can actually, on your desktop, analyze easily 20, 30, 40 million rows in RapidMiner without any problem. And if that's not enough, there is the Hadoop product to actually push into Hadoop clusters. So there is no particular reason inside of the platform why people should analyze smaller data sets. But good observation, now in a year from now, we should actually see kind of like a wall at the 10,000 because, yeah, okay, we changed the behavior of people now, yeah.
Okay, thanks.
Absolutely.
Thank you.
Thank you.